Good morning, everyone, and welcome to ICLR 2019. My name is Alexander Rush, and I was this year's Senior Program Chair. So I want to begin the conference by acknowledging the winners of the 2018 Turing Awards, Jan LeCun, Jeffrey Hinton, and Joshua Bengio. This is the most prestigious award in computer science, and it's incredibly exciting that this year it was given to these three pioneers in the field of deep learning. So let's give them a huge round of applause. So ICLR 2019 was put together by the following program team. Our general chair was Tara Sainath, and our program chairs were Shakir Mohammed, Sergey Levine, and Karen Levescu. We worked together to put together the program for this conference, and I hope you guys will enjoy it over the next 4 days. This year at ICLR, we also have a workshop session. The workshops will run concurrently to the first day of the conference, and you can follow the signs to get to them upstairs. And this program was put together by Bean Kim and Graham Taylor. Additionally, this year, ICLR has two diversity and inclusion chairs, Alice Oh and Rich Zemmel. And I'll talk about some of their work later in this talk. The organization for ICLR, including this amazing venue, was put together by Andrea Brown, Lee Campbell, and Brad Brockmeyer. Additionally, as you all know, ICLR has a unique reviewing process, and we rely on the amazing work of the Open Review team. The Open Review project is run by Andrew McCullum, and we also work closely with Michael Spector, Melissa Bach, and Mohit Uniao. ICLR also thanks its sponsors, and you can see their booths in the room, I think, to the left of the stage. So normally, the first 10 minutes of the conference, I would talk about some of the statistics that went into the reviewing process, what's hot this year and what's not, and how big the conference has grown. We have about 1,590 submissions and over 1,400 reviewers. So I think these are interesting, and I put some of the statistics online for people to look at. But what I would like to do instead is to spend this time talking about a different topic. And the topic I want to talk about are the questions of diversity and inclusion in the field of deep learning. So this is a slide from my colleague Timnit Gebru that was taken in a session from ICLR 2018. When I took over this role, I talked to her a bit about some of the challenges that deep learning faces in terms of diversity and inclusion. And one thing she said that struck me was when we think about questions of intersectionality and diversity, she's someone who identifies as being female, as being black, and as being a refugee. And when she looks out in the audience at a conference like this, it's not clear where someone starting in the field with that background would feel like they belong. So this year, we tried to take some of these ideas to heart. We made some active and direct steps to try to work on making ICLR and deep learning in general a more diverse and inclusive field. This year, we have events from Women in ML, Black in AI, Latinx in AI, Queer in AI, and several other groups. All of these are self-organized, and I give credit to the leaders of these communities. We have 100% gender parity in our program team, invited speakers, and session chairs. We gave 50 additional student travel awards strictly on the basis of underrepresentation in the community, on top of travel awards for people with papers. When deciding workshop chairs, we took into account factors of diversity, and all workshops have at least 2 female organizers. We introduced an ICLR Code of Conduct for the first time, which is available online. And we took minor initial steps to try to improve diversity in our area chairs, going from 13% to 25% female representation. Now, for the sake of transparency, I want to just say that these are easy and first steps, and that there's a long way to go. And it's worth knowing, or it's worth everyone in the community knowing, what some of these challenges are. So I want to talk about some of the major issues in the field. So the first is one I think probably everyone knows, which is the challenge of gender diversity. But it's really worth knowing how far we have to go on this problem. In terms of this conference, the presenters for oral and posters are only including 8.6% female presenters, and registration only goes up to 15%. This is a really bad problem and a really stark issue, and it's everyone's responsibility in the field to think about. Another problem we face is racial diversity. We have a continuing issue that we didn't have any invited technical speakers who were from underrepresented racial groups. And we were called out about this from some of the affinity groups in these areas. And I think we take a lot of responsibility for that failure. There's a rich and vibrant community of self-led affinity groups, but we need senior leaders, and we need ways to support and sustain these communities. Another related problem is geographical diversity. This is a log scale map showing where attendees to this conference come from. We have continuing most of the presence from North America, Western Europe, and a growing community in China. But for this really to be an international community, we need to work on ways to make it easier for people to attend this conference and to give them better reasons to come. One thing that's exciting on this front is that next year, ICLR 2020 will be hosted in Addis, Ethiopia, which is a really exciting change, and it will be really exciting to have a major machine learning conference be hosted in Africa. In preparing for this conference, we also talked with LGBTQ leaders in the field, and we particularly talked with leaders of the group Queer in AI. They sent over some statistics they thought were important for people to know, and I must admit I wasn't aware of all of these numbers. They said that 2/3 of queer researchers are not professionally out. 50% have experienced harassment in their professional life, and 40% say they lack senior leadership and role models in the field. We don't talk enough about how this is a barrier for people feeling like they have a career path and feeling like they're included in the area itself. One issue that I should be honest about is that there is probably justified backlash from this community about feeling like they might not be safe attending a conference in Ethiopia. However, we hope, and there's been ongoing conversations between this community and organizers in the field, to work with the government to make these researchers feel safe. And we hope to use this as an opportunity to increase the presence and increase the community that goes around Queer in AI and other groups. So I bring this up not because I think these are impossible challenges, but because I think they're difficult in ways that we can manage. Many researchers view themselves in this intersectional lens, and many of these problems intersect in ways that are both hard and kind of challenging. But ICLR is a new community. We're growing at a tremendous rate, and there's a tremendous amount of energy that can go into these challenges. I hope we can look back in 10 or 20 years and see these as early growing pains of the field. Now, I want to end by talking about some of the small behaviors that we can all partake in to foster inclusion in the community itself. And I picked these three because these are all areas people on the program team have admitted to failing on in the past. And I know I personally have failed in all three of these regards. So the first is to be extra supportive, particularly when you feel there's a power imbalance. 60% of the people here are attending ICLR for the first time, and keep in mind what it felt like to present your first poster. Go out of your way to be an ally. This can both be in terms of small things, like referring to someone by their chosen pronoun, but also more difficult challenges, like speaking up even when you feel like you're not the one being put in a bad position. Finally, when possible, avoid going to exclusionary events or having exclusionary conversations. It can feel good for a second to get some invite somewhere, but it makes it very hard for new people to the conference to feel like they belong or that they're welcome in this community. Now, to end, I want to talk about some of the inclusive events we set up to make everyone's first day at ICLR 2019 even more welcoming. One thing is these workshop sessions that will take place during the first day of the conference. ICLR is generally a pretty big room, and so if you want to seek out people who are more within the kind of sub-discipline you work on, workshops are a great way to talk to people in a smaller setting and get to know people at the conference. We also have an opening reception and newcomers event that will take place from 6:30 to 7:30 tonight. Furthermore, there are events from Women in ML, Black in AI, Latinx in AI, and Queer in AI, and they're all available if you go to our website. Finally, we have an app at this conference that you can download called Whova, and there's already a ton of conversations going on about different people with different sub-interests trying to get to know each other at the conference. And finally, if there's any issues that come up, we set up a hotline, iclearhotline@gmail.com. Feel free to send that, and the diversity and inclusion chairs and the program chairs will see your email. Okay, with that, welcome to ICLR 2019, and I hope we have an amazing 4 days. Thank you very much.
Hi, good morning and welcome everyone. I'm Katerina Fragiadaki. I'm the chair of this first session. I will introduce our first keynote speaker, Cynthia Dwork, who is a Gordon McKay Professor of Computer Science at the Harvard Paulson School of Engineering, Radcliffe Alumni Professor at the Radcliffe Institute for Advanced Study, and affiliated faculty at Harvard Law School. Cynthia uses theoretical computer science to place societal problems on a firm mathematical foundation. She was educated in Princeton and Cornell. She received her bachelor's with honors in electrical engineering and computer science at Princeton University, where she was also received the Charles Era Young Award for Excellence in Independent Research, the first woman to ever do so. She received her master's and PhD degrees in computer science at Cornell. In 2007, she was awarded the Edgars Dijkstra Prize in recognition of some of her earliest work, that established the foundations on which every fault-tolerant system has been built for a generation. She has several contributions to cryptography, including the launching of non-malleable cryptography, the subfield of modern cryptography that studies and remedies the failures of the cryptographic protocols to compose securely. She is also a co-inventor of the first public key crypto system based on lattices, the current best bet for cryptographic constructions that will remain secure even against quantum computers. Cynthia is known recently for the co-invention of differential privacy, 2006, now the subject of intense activity across many disciplines, and the recipient of the Theory of Cryptography Conference 2006 Test of Time Award. Differential privacy has recently been introduced in Apple's operating system, 2006, and in Google Chrome browser in 2014, so it is just beginning to be deployed on a global scale. Cynthia, along with her co-authors, Frank McCherry, Komi Nissim, and Adam Smith, received the 2017 Gödel Prize for their seminal paper of 2006 that introduced differential privacy. More recently, Cynthia has been working on algorithmic fairness. Data, algorithms, and systems have biases embedding within them, reflecting designers' explicit or implicit choices, biases, and societal priorities. These biases result in unfair algorithms. For tasks ranging from advertising to recidivism prediction, and consequence of such unfairness has recently attracted considerable attention in the popular press. Cynthia, anticipating these concerns, initiated in 2012 a formal study of fairness in classification, and she will talk to us today about this work since then. Finally, Cynthia is a member of the US National Academy of Science, the US National Academy of Engineering. She is a fellow of the ACM, the American Academy of Arts and Sciences, the American Philosophical Society. We're very excited for being here. Without further ado, Cynthia Dwork.
Good morning. Thank you for that very kind introduction. Thank you for inviting me to speak here. This field more or less began around 2009, 2010, 2012, and I want very much to tell you about extremely recent developments. So this is a brand new talk. We'll see. All right. So this is a picture of Joy Walamwini demonstrating how a facial tracking system fails to detect her face until she puts on a white mask. You all know that algorithms are unfair, that the training data may be unrepresentative. For example, it may have few black women. The training labels can embody historical bias. The features selected for the algorithm to make decisions on can be differentially expressive in different communities. For example, 0 AP classes means something very different in a poor district that does not offer AP classes and in a wealthy district that does. Now, algorithms have life-altering consequences. For example, mortgage terms, detention release decisions, medical assessments and care, and in an example that I'll talk about for a bit over the course of this lecture, whether or not a child is removed from the home. So in her book, Automating Inequality, How High-Tech Tools Profile, Police, and Punish the Poor, Virginia Eubanks devotes a chapter to the Allegheny Family Screening Tool, which is an algorithm deployed by the Allegheny County Office of Children, Youth, and Families to forecast child neglect and abuse at a hotline. I should note that decisions whether to screen a call in or out are not made entirely by the algorithm. Human call screeners first make their own clinical risk assessments, then they see what the algorithmic risk assessment score is, and finally, the human will make a decision unless the algorithmic score is too high, and then the call is automatically screened in. And later, we'll give examples of differences in the kind of data collected and available about the poor versus about the well-off. But for now, I just want to comment that the outcome variables are not fatalities, near fatalities, or even substantiated child abuse. They are proxy variables that are community referrals, which means that a call to the hotline was initially screened out, but another call received on the same child within the next 2 years. And child placement, which means that a call was screened in and results in child placed in foster care within 2 years. So the algorithm is actually predicting decisions made by the community and by the agency and the family courts, and not whether or not the children are actually harmed. Now, there are a lot of papers that basically say this, okay? I'm shocked that there is bias in algorithms. And we'll see examples of them. And it is shocking. But this is now something that we really know and we really understand, and we have to do something about it. Now, the field of algorithmic fairness is exploding, but it's also experiencing growing pains. There are many definitions of fairness, and many natural desiderata have been shown to provably conflict and not be achievable simultaneously. Moreover, even at the very best, the algorithm is just one piece in a vastly unfair world. And an example of this is again in Allegheny County, where we see that the algorithm can be deployed in a disparate fashion. So although in 2016 African American children made up only 18% of the county's children, 48% of the children in foster care were African American. And Eubanks writes that the great majority of disproportionality in the county's child welfare services arises from referral bias, not screening bias. So again, the way in which the algorithm is deployed can also introduce bias. Now, my approach as a theoretical computer scientist was to try to establish a theory of fairness, a theory of algorithmic fairness. So one of the first things that we would do is to sit down and try to come up with a definition of fairness. And for the most part, in this field, definitions fall into two broad categories: group fairness definitions, which are the vast majority, and individual fairness. Later we'll see yet one more type. So, group fairness definitions are basically statistical requirements about the relative treatment of two different groups, typically framed as two disjoint groups. So an example of a group fairness condition might be that statistical parity. If you're accepting students to a college, the demographics of the accepted students should be the same as the demographics of the population as a whole. Another popular one, often called equalized odds or balance for the positive class, says that if we have a classifier C that is classifying individuals X, the basically probability that a positive member of S should be classified positively should be the same as the probability that a positive member of some other group T would be classified positively. And while group definitions may have place in specific contexts, group definitions typically fail actually under scrutiny. So there are a number of papers about that. Now, in contrast to the group definitions, in the original work on this, we looked at individual fairness. So individual fairness says intuitively that people who are similar with respect to a specific classification task should be classified similarly by any classifier for that task. So that's pretty natural. And it has a strong legal foundation. There's a concept in law of similarly situated people being treated similarly, and this falls right in with that. And it is a powerful framework. If you can know who is in fact similar to whom, or a little more precisely, given two people, what is their degree of similarity or dissimilarity, you can build a very powerful framework that lets you do a lot of things, and that was the subject of the first paper. But the drawback, of course, is that we need this metric, this task-specific metric that tells us how similar or dissimilar individuals are for a given task. And where's that metric going to come from? That's not an easy problem. And this, of course, accounts for the vast explosion of work on group fairness and the relative paucity of work on individual fairness. Nevertheless, the last couple of years have turned up several interesting results, and I'm going to talk about one of them briefly. So this is work of Cristina Ilvento, my student at Harvard. Cristina, by combining ideas from the HCI community and techniques from learning theory, came up with a way of using a human adjudicator to derive an approximation to a metric. So the adjudicator has some kind of intuitive mapping from some high-dimensional feature vector, like X in this example, to what are really somehow intuitively the important aspects of the problem. And there are two kinds of queries. There are sort of relative distance queries, which are easy for humans, and this is from the HCI literature. So given individuals A, B, and C, it's an easy question to determine which of A and B is closer to C. And then there are the hard queries, which are the absolute distances. Given A and B, what is the distance between A and B? And what Ilvento does is come up with an approximation, an algorithm for approximating the metric with only a constant number of hard queries. So that's quite remarkable. And there are three insights in her work. The first is that distances from a single representative element produce useful approximations to the true metric. But just having that, you can't distinguish sort of elements on either side of this representative element A. So in this picture, on the left, H and C are at distance 0 from each other, and on the right, H and C are at some big distance from each other. And just knowing distances from A doesn't let us determine which of these two is the case. And essentially what she shows is that this sort of parallax, which is what you need there, can be achieved by aggregating approximations obtained from a small number of additional representatives. And finally, she shows that you can generalize to unseen elements under some simple assumptions about learning threshold functions. So I think this is a very exciting and very promising direction of research. And as I said, these are very recent results. So this is 2019. Now, a different direction was introduced in two parallel works that were done independently, both in 2017, which I am calling multi-X. So this is an attempt, both of these are attempts to bridge the group versus individual gap. Both groups looked at simultaneously achieving group fairness, but not for a single pair of disjoint groups, rather simultaneously for every pair of sets in some very large collection of pre-specified sets. And that's what I've drawn in gold there. So I call these multi-X because X is going to name the group fairness condition that we're interested in keeping across the different pairs of groups. And multi is to remind us that we're talking about the intersectional case, large numbers of large and intersecting groups. Okay. Then some of these results were applied by Kim Gorbani and Zhou, for example, in problems like addressing the gender shades issue that I spoke about earlier when I mentioned Joy Wong-Weenie. And more recently, we've been looking at ranking, and time permitting, we will get to a discussion of these concepts in terms of ranking. So in the remainder of the talk, I'm going to focus on multi-X in scoring and ranking. And finally, because this is ICLR, I'm going to end with some recent results in censored representations. I'm also really excited about those, but they're work in progress. Now, many scoring functions produce scores between 0 and 1, which are commonly viewed as probabilities. So we talk about what is the probability that this individual is going to repay a loan, or what is the probability that this tumor will metastasize? What's the probability that it will rain tomorrow? What is the probability that this person will commit a violent crime? Okay. Well, it's just not clear what this means. What are these individual probabilities when we're talking about an experiment that doesn't get repeated? What is the definition of probability in that case? And my personal motivation is, supposedly being knowledgeable about algorithmic fairness, what happens if I have to go to court and explain this is the meaning of the score, this is the meaning of the probability risk assessment, and why would I be comfortable with my answer? So if you come from a cryptographic background, you say, oh, this is simple. I have an individual X has some internal randomness, X interacts with an environment, the environment has some randomness, and the probability space is just the joint probability distribution of the coins of the individual and the environment. But when you leave the filter bubble of cryptography, nobody believes that, or very few people believe this unless perhaps you're a Bayesian. Then it's the alternative. Okay. Now, this problem is hardly original, and for example, in 2018, I think motivated by exactly the same situation that I described of the recidivism predictions, Philip David, who has been writing about these issues for since the early 80s, wrote a survey of a variety of possible explication of the term individual risk. And to cut to the chase, he basically says he's examined a multitude of explications and approaches, and he modestly concludes that the concept remains elusive, although perhaps some suggestions for progress are made. We'll see one more suggestion for progress later in this talk. Now, when people think about individual probabilities, one thing that they think of is calibration. Calibration is a concept that arises in forecasting. So just think about the problem of forecasting rain for the next day. So every day the forecaster makes a prediction. What is the chance of rain tomorrow? So it might be 50% chance of rain, 70% chance of rain, and so on. Calibration says, roughly speaking, that if you look for any value V, say 70%, you look at all of the days on which the prediction was V, then in fact a V fraction of those days should have rain. So 70% of the days on which the forecast was 70% should have rain. 30% of the days on which the forecast is 30% should have rain. And much of the literature on forecasting views this as the sine qua non of forecasting. You can't be a good forecaster without this. Okay. So this is a really interesting concept, and we will come back to it. But to sharpen our intuition a little bit, let's think about the case of a tumor. So here's a tumor, and the question is, what's the chance of metastasis under a given course of treatment? And my numbers are completely bogus and made up. So suppose you have two different studies. One study of tumors looks at certain locations in the genomic information, so certain gene expression levels of the tumors, and concludes that 40% of the tumors that have these gene expression levels metastasize under this course of treatment. And a different study, looking at different features, may give an expectation of 70%. So what do we conclude about this tumor? Okay, notice that if all we have are the expectations and not the training data, we really can't say anything. If we have the training data, maybe we have examples in the intersection that will give us some statistics for tumors in the intersection of these two studies. Not in this training, not that any individual is in there, but the conditions are met by both studies. Okay? So there is a difference of having training data and just seeing expectations. Now, given just the expectations for the sets in a collection, which I'm going to call S1 and S2 here, we can choose values for the elements in these, these regions, P, Q, and R, so that the expectations for the sets S1 and S2 are preserved. And that's essentially a linear programming problem. So we call this multi-accuracy with respect to the collection C of sets. So any predictor that retains the expectations for the sets in the collection C is called multi-accurate. Now, there can be many multi-accurate solutions from which to choose. In other words, just those two expectations for S1 and S2 don't totally nail down what the options are. So, for example, suppose both in sets S1 and S2 the expectation is 0.4. You might think that we should conclude that everybody has a 0.4. The statistics for the three different sets is now 0.4. But there are other possibilities. So for example, if P, Q, and R all have the same cardinality, maybe if you're in the intersection and you have both of these features, you're really, really at risk, and the probability for you is 0.6. And if you're out in the wings, then the probability is only 0.2. Or another possibility is exactly the opposite, that somehow these two things cancel out and we have 0.2. So we really haven't nailed anything down. But we can see that if we had at least calibration, then this would help. It would help us resolve, for example, whether it's 0.2 in the intersection or 0.6 in the intersection. Because calibration says that if it's a 0.2 here, that a 0.2 fraction of the people that are assigned the score 0.2 in fact have the property. Okay. Now, let's look at the lone example for a minute. So, again, we have intersecting demographic, ethnic, age, gender, sexual preference, mental health, physical health, et cetera, groups. And at the least, we want loan policies that are consistent with the expected repayment rates for each group, where the expectations should be determined by historical binary outcome data. This is an example of This is kind of a minimal requirement. It's find out what the history says, be evidence-based in this regard, and then maybe you want to do some adjusting because of historical trends. But first, find out what the data are telling you. So that's why I say minimally we want this. Now, the question comes up, which groups, which sets should we have in our collection? So who decides that? Is it the culturally dominant that make that decision? Or the people in the oppressed minority groups? Do we put it on those of us in the oppressed minority groups to insist on our rights? And that's really problematic because oppressed groups tend to internalize the views of them, or of us, held by the dominant group. So that doesn't make any sense either. And this is where I just love complexity theory. Suppose we say that the sets that we're going to care about are all of the sets that we could identify by applying small circuits to the data that we have. So everything that you could efficiently compute about somebody. Or maybe instead of small circuits, maybe you liked short decision trees. But you get the idea. It's a class that is complexity-based. So the conjecture is that this should capture all historically disadvantaged groups. But it highlights a requirement from the data that we already questioned at the beginning, a kind of equally rich expressiveness over the different groups. It requires that the data should be sufficiently rich to permit identification of members of each of these groups with reasonably high accuracy and specificity. Okay, now the key point here is that we can do this. The complexity of creating the scoring function will depend on the hardness of agnostically learning the collection of sets C. But the function, once we have it, is efficient. And this is the work of Aber Johnson, Kim Reingold, and Rothblum. So that's multi-accuracy. They go one step further. They require, in addition to multi-accuracy, that the function should actually be calibrated not just overall, but on each of the sets S in the collection individually. So that means that the predictor, first of all, by multi-accuracy, will be accurate in expectation over all the sets S and C, which are fixed in advance, but also it will be accurate in expectation over all sets S sub V, which are those in the set S assigned V under F. So it's calibrated on each set S in the collection simultaneously. So that's extremely powerful. And yeah, okay. The devil here, of course, is in the collection C. So what we're assuming is that it's everything that's efficiently computable about an individual from the data, and our hope is that we're capturing all of the task-specific, semantically significant differences. That this collection is somehow rich enough to show who are the really college-ready students, even in a school that does not offer AP classes, for example. But we do have to worry about the data being differentially expressive. The good news is that we think we have a test for this. But as I say, this is work under, in progress. So that's careful. I should mention, as an example of data being differentially expressive, I promised you this at the beginning of the talk. Here again from Virginia Eubanks, she talks about what are the sources of information that are available to the Child Protective Services at call screening. So the things in red are things that typically are used by poor people. So the capitalized drug and alcohol this is the state drug and alcohol services, Head Start, mental health services, the housing authority, also information from the jail, Pennsylvania's Department of Public Welfare, Medicaid, and the public schools. Now think instead about people who are well off. They might have private drug treatment, private mental health, nannies, babysitters, private therapists. They may go to Alcoholics Anonymous, rehab centers. They'll have private financial support, private health insurance data. So there's a tremendous difference in the kinds of information and the amount of information available about poor people versus about rich people. Okay, next part of the talk. I want to talk about fair ranking. So ranking is just ranking, like ordering people. Ranking is the heart of triage. You've got an emergency room and you have to decide who is going to get treated first. Ranking is often the underlying impetus for scoring. So for example, you want to admit students to a university, you rank them according to whatever criteria you have in mind, and then you take the top blah fraction. So as such, ranking or thinking about ranking can tell us more about what we want from a scoring function. We've talked about some things we can get from a scoring function, like multi-accuracy and multi-calibration. Is there something else that we want? So looking at ranking can help us answer that question. Also, some affirmative action strategies can be thought of as working from rankings. I think of this as merge sort. So something that's done by California and by Texas is the students are ranked at within each high school by, let's say, grades and test scores. And then the top 10% are admitted to the state university. So this is sort of a merge sort. Another possibility in the fabulous work by John Romer talks about stratifying children by the education level of the mother and then ranking them according to how much time they spend on homework. And that was very counterintuitive to me when I first read it. I thought, well, if you have to spend a lot of time on homework, then maybe you're not as good as if you only had to spend a little time on homework. But no, this is entirely the wrong way to be thinking. And he points out that students from a very uneducated family may not even realize it's possible to spend 8 or 10 hours a week studying. Okay. Also, if you're an experienced clinician, a rank may just translate automatically to a score. So if it were to turn out that ranking is easier than scoring, then that could be useful. So if you're an experienced clinician, you may very well know if you see that somebody's in the top 10% of risk, what that number actually translates to in terms of probabilities. So approaching this from a typical cryptographic perspective, when we think about trying to carry out fair ranking, we imagine that we have a ranking adversary, or like, what is it that we're trying to prevent? So here's an example of something that we obviously would want to prevent in a fair ranking system. Suppose you have two, let's say, disjoint groups of people, A and B, and on average, the people in group A are more highly qualified than on average they are in group B. Clearly, any ranking that put everybody in B ahead of everybody in A is unfair. So, interestingly, if we were to build a multi-accurate predictor, which now gives us a score for each individual, and we rank them according to those scores, any multi-accurate predictor would rule out this particular kind of unfairness. So we see a connection between a particular kind of evil that we'd like to handle, where we think about sets of people, and we connect it to something having to do with scoring functions. And this led us to create two different hierarchies. One of them is to build up these sets of examples. So at the bottom level of our hierarchy, We have generalizations of what I just showed you, the evil that I just showed you. At the next level, we have that and a few others, and at the next level, we have that and a few more. So the rankings will preclude these sort of nested collections of evils in the relative treatment of pairs of sets. And in the other hierarchy, we look at rankings that are consistent with scoring functions of a particular type. And what we came up with showed that the top level of these hierarchies are equivalent, and they're actually achieved by consistency with any multi-calibrated scoring function. So we came back to multi-calibration again, almost by accident here. And what this tells us is that any stronger requirements will arise only from the choice of C and the kind of data, as in the example of the Allegheny County algorithm, the screening algorithm. And they won't come from the relative treatment of the sets within the collection. So this focuses again our attention on what's being measured and what's being collected as where the heart of unfairness is going to lie. And I'll just note that this also gives us a perspective on individual probabilities. So we are exploring a possible approach through complexity theory. If positive and negative examples were actually computationally indistinguishable, then the best thing we could possibly do is to assign to everybody a probability according to the base rates for the populations. But if the set C is very rich, so in this other context, if we have multi-calibration and the set C is very rich, perhaps in analogy, it's legitimate to treat any C multi-calibrated prediction function as if it were the truth. And so it's basically an analogy to pseudo-randomness with respect to the tests embodied by the sets in C. And again, we have to worry about justice. We want to be sure that C is not differentially expressive. So my last couple minutes, I'm going to talk about representational approaches. A number of years ago, we looked at the idea of learning a fair representation. So we define a fair representation. So what we had in mind was that we would find a representation for individuals that will stamp out sensitive information, in particular group membership, but it would retain enough information to permit standard training. Now, I should say this is group fairness, and as you know, I'm not wildly enthusiastic about group fairness, but we did some work in the early paper to at least see whether similar people ended up treated similarly. Follow-on work has stopped looking at whether similar people are treated similarly, and I would urge you to go back to that. So this work was sort of picked up and some beautiful paper by Edwards and Storking, which looked at the adversarial version of what we had begun. So they too want to learn a censored mapping from our input space X to a lower dimensional space Z. And in this picture, I have a minority group S in yellow, and then there's S complement, which is the rest of X. So the idea is to learn this censored mapping, and the encoder will try to hide the membership bit in S, but still permit prediction on Z. And the decoder will try to reconstruct X from the encoding of X, so from Z. And the adversary, who is helping along with this process, will try to distinguish encodings of members of the minority group S from encodings of the complement of S. And that's how the censoring works, through the adversary. Recently, Madras, Krieger, Patasi, and Zemmel extended this work, and they did two things which I found very exciting. First of all, they wrote down a couple of different objective functions which correspond to different notions of group fairness. So for example, statistical parity, the equalized odds notion that I mentioned earlier, and at least one more. And they then prove that sort of in the limit, with the training of the adversary, they will actually, their objective function really does capture exactly these goals, that you'll settle on exactly achieving these fairness goals. And what they were very interested in was the fact that they could learn a representation that in some sense had been very well censored, but was so rich that not only was it enough for the task at hand, but it could also transfer to other tasks. So they called their approach laughter, and the TR at the end refers to transfer learning. Now, we're going to build on the laughter approach. So in 2015, Giovanni Parmigiani, a biostatistician at Harvard, introduced me to what I will call the Harvard-Stanford problem. The problem is basically this. Suppose you're at Stanford and you build using really good AI, an algorithm for predicting metastasis of tumors. And your algorithm does what it's supposed to do, and it generalizes well to the population that comes to the Stanford Hospital. At Harvard, we could do a similar thing. So we assume that that's done as well. Then Giovanni told me that the algorithm developed at Stanford won't work on the Harvard population very well, and the Harvard algorithm won't work on the Stanford population very well. And there are two sources of difficulty. One is some differences in the populations, and the other is differences in lab preparation techniques. Okay. Now, the goal in the current work is, which is still in progress, is to apply the laughter and censoring techniques to learn what is common across the different populations. So not to let the algorithm get distracted by things that are specific to these different labs and groups, but rather to find what is common. So my oracle on this, Giovanni, says this is a reasonable thing to do when you're looking at these kinds of biostatistical problems. And notice that we don't need to do this for the benefit of the Harvard population or the Stanford population. The goal in this work is to learn what is common to humans across these different well-studied populations in order to have an algorithm that can work on members of remote communities for which we have zero training data. So it's a form of out-of-distribution generalization that we build up by looking at multiple distributions. So we get a problem that looks something like this. We have our domain X, which has these different populations, and we're trying to learn what's common among them using the same laughter code base or approximate code base to find something that will work on new populations. So what we did was exactly that, and we did this for synthetic data for now. As I said, this is very much work in progress. So we built 4 different synthetic populations for training and a 5th one for testing. And here's what our synthetic data look like. We split the data element into 2 fields. The first one is capturing what's common among the populations, and the second, X2, is capturing what is population specific. And to generate a data element for various functions F that were chosen along lines that were used by Parmigiani and Patil in their PNAS paper, Training Replicable Predictors in Multiple Studies, we proceeded as follows. First, we choose a label according to the base rate of our population. So we allowed different base rates for the different populations. And then we choose data elements X from a multivariate Gaussian, and we ensure that the label is encoded both in the common features and in the population-specific features. So specifically, we retain X if a certain stochastic test based on the common features indicated by this Bernoulli of a sigmoid of F1 of X1 yields the label Y, and a deterministic test based on the population-specific labels, features also yields Y. So we have different tests for the different synthetic populations, F21, F22, and so on. So this actually makes the population-specific test stronger and better than the common test. And here are some pictures of what we found. So when the functions that we use are all linear, there are some settings in laughter for which laughter does better than a baseline of logistic regression. But when we introduce interaction terms, in this case, two product interactions and two binary threshold interactions in the common and in the study-specific cases, we get much better behavior under laughter. So we think this is a promising approach, and we're excited to pursue it. So to just go over what I've covered, we've covered an incredibly large amount of ground. We saw through examples that a fair algorithm is at best one piece in an unfair world. We saw a breakthrough in metric learning for individual fairness, and we examined scoring functions in the multi-X approach. We saw the significance of multi-calibration to the problem of fair ranking, and we noted that it focuses attention on the representation embodied by the sets in the collection C. This is your bailiwick, this representation in the set C. And we suggested that it might provide an approach to understanding individual probabilities via the theory of indistinguishability and pseudorandomness. And finally, we showed that censored representations yield an approach to out-of-distribution generalization when there's reason to believe there is a common signal across populations. Thank you.
Yes, thank you for the great talk. Are there any questions? Please line up on the microphones. Okay, let me ask one question. In computer vision, we would be happy if our algorithms were as good as humans to perceive the world. Would you be happy if these algorithms were as fair as humans, or do you want to make them superhuman in fairness? Because we know that humans are super unfair in decision making.
So I think that ultimately I want it to be super, super fair, but at the moment, I think that I think we don't even understand what fair is, and the best we could do is sort of the best trained and judicious people that we have available. So that would be my benchmark now. I think I'm
Okay, let's thank our speaker again. Thank you very much. Okay, so we go ahead with the first contributed talk, generating high-fidelity images with subscale pixel networks and multidimensional upscaling. Jacob Mennick is the presenter.
All right. Hey, everybody. I'm Jacob Mennick from DeepMind. This is joint work with Noel Kalkbrenner from Google Brain Amsterdam. And I'm going to tell you how we scale up autoregressive image models to big images and also get nice samples. So the way we're framing the problem is we're working with likelihood-based models. So we want to capture all the diversity and variation in a given data distribution. and including every detail in every image. And this can be important in cases when we don't know a priori what it is about the data that we're going to care about. So for instance, for producing nice quality visually nice samples, maybe high frequency information doesn't matter, or maybe all of the bit depth of an image doesn't matter. Whereas for object recognition, maybe the position or orientation of objects doesn't matter. But without assuming a priori what task a model is going to be used for, we don't know what bits don't matter. So in this problem setup, we're going to aim to model everything. But we're still we want to model all of this variation while still keeping high quality samples. And this convinces us that all the structure has been picked up successfully. That means no artifacts like blurring, which is commonly played, likelihood-based models, or stitching artifacts or anything like that. Just nice, high-quality samples. And the hope is that these kinds of models can eventually be useful for, semi-supervised learning with a small amount of labeled data, or planning and reinforcement learning agents, or these kinds of things. But the models we're working with are deep autoregressive models, and again, we're working with these because they're forced by their objective function to cover the entire data distribution. And the sequential nature of the sampling process means that the models have nice details, the samples have nice details by default. So what is an autoregressive model? The typical, an autoregressive model lines up all the pixels in an arbitrary ordering, say the raster scan ordering, which is in this slide, which starts in the top left, moves along a row, and then goes row by row. Like I said, the default behavior of these samples is to capture details, but the challenge is to get global coherence from samples from these models. So the issue is that since each pixel gets to condition on some context, the challenge is to capture all of that context adequately to maintain a single global sample for the entire image. And this is both a modeling challenge and a computational challenge. The technical challenge is how to basically train big enough networks with enough capacity to capture all this variation. And the dominant type of architecture used in autoregressive image models is so-called resolution-preserving architectures. So what this looks like is basically the image to be modeled comes in as input. There's a stack of some sort of masked operation, like masked causal convolution or masked self-attention. And the whole way up the network, feature maps are shaped like the input. And out comes, at the output layer, this conditional distribution for each pixel. And the problem is, as you scale up the size of images, the memory usage, since each feature map is as big as the image, the memory usage just blows up. So, and especially for self-attention, it basically becomes intractable for large images, which is why we've seen a lot of research into some cheaper approximations, like using only local windows or using sparsity, et cetera. So this work has two contributions which aim to mitigate these scaling issues. And the first is the subscale ordering. And the way it addresses this modeling challenge and computational challenge is kind of intertwined. So what is the subscale ordering? We take an image, which is diagrammed on the left, and split it up into sub-images, which we call slices. And the ordering proceeds proceeds slice by slice. And so a slice is, we proceed in a slice in the usual raster scan order, but the slices are kind of interleaved in the original image. So when we get to the second slice, each pixel in the second slice can condition on all the pixels of previous slices. And again, it's the usual order. But the effect, so if you think about what is a slice, it's kind of like a downsampled image. So when you're sampling the second image, you're basically doing a kind of upsampling. And the hope is that working in this order makes the subsequent slices an easier modeling job. Okay, and the second core idea is this idea of multidimensional upscaling. So whereas the subscale ordering intrinsically has this kind of size upscaling, we also do channel bit depth upscaling. And what that is splitting each pixel in half, basically, into the coarse bits and the fine bits of its intensity integer representation, and lining up all the coarse bits first, and then only after the coarse bits have been generated, generate the fine bits of that same image. And so we can chain these ideas together. So the first thing that will be sampled is a small coarse bits of an image, and then the full-size coarse bits of the image, and then the full-size, full-resolution image. So the ordering I've shown here compared to the raster scan and how to combine these ideas together. The different colors indicate weight sharing in the architecture, which I'll tell you about in just a moment. So the architecture, the main difference from past architectures is that it has two parts. One is an embedding network, which when we model so we model one slice at a time with the usual autoregressive decoder. But there's this extra embedding network which gets to condition on the previous slices. And the crucial thing is that all feature maps when we train this network, every feature map is shaped like a slice, not shaped like a full image. And that means we can use full self-attention, since we have control over the slice size. So for instance, when we model 128 by 128 images, we fix the slice size at 32 by 32. And ditto with 256 by 256. And so that's kind of the crucial scale. That's what makes this architecture scalable, basically, is that we can get past these spatial scaling issues. And so we kind of take advantage of these scaling properties to operate at a large scale. So we train on TPU v3 chips. We use our biggest networks used 256 tensor cores for a training run. And the architecture has 250 million parameters in its biggest form. I should say also that we actually train two subscale pixel networks, one with its own weights for the coarse bits of the image, and one with its own weights for the fine bits of the image. So a single sample will use up to like 650 million parameters just from these two different networks. We can also dedicate a decoder just to the first slice, just a single unconditional decoder just to the first slice of the image, and that adds a few, maybe 50 or 100 million parameters. That's where that 650 million figure comes from. So that's a pretty large scale, and we basically get we get a really nice improvement in sample quality for likelihood-based models, and indeed, past autoregressive models simply couldn't run on these resolutions. This is 256 by 256 Celebet HQ, and so this is a sample from our 3-bit model. And with the bit depth upscaling, we're eventually outputting the full sample resolutions. We're not making any, we're not throwing away any bits in the data. Unsurprisingly, we improve log likelihood numbers in these high resolution data sets, so ImageNet 128 by 128 and 256 by 256, because we know autoregressive models tend to get the best likelihoods. And this is kind of about opening up new domains for autoregressive models by solving these scaling problems. So we see nice improvements over models which either aren't fully autoregressive or aren't autoregressive at all, like flow-based models. Another interesting point is that this bit depth upscaling trick doesn't really affect likelihoods, but it does give a nice improvement in sample quality. So back to this point about the extra decoder trained on just a single slice. The insight there is that it's basically useful to have enough capacity for the very first pixels that are sampled are important to get right, because if you mess one up, then pixels later in the ordering are conditioning on a kind of bogus context. So this is what 32 by 32 samples look like from that single unconditional decoder. And then when we run them through when we continue sampling from the unconditional, from the SPN, we get to the full resolution. And these are unconditional ImageNet samples, which you don't often see, actually. So many of the nice 128 by 128 ImageNet samples you'll see are conditioned on a class label. We can also do that. It's a really simple tweak to the architecture. And the samples are also a bit nicer. And I've kind of lost track of time. I don't know how much time I have left. Okay. Cool. Thank you. So yeah, in conclusion, there's been nice progress in these types of models over the past couple of years, especially if you look at the unconditional case. This is just from 2016 to late 2018. We can pretty much, we've made nice progress towards solving these scaling issues. We have globally coherent samples, and we know because of the objective function that they capture all this variation in the data set. And yeah, thanks for your attention. I'll take questions.
So we have 2 minutes for questions.
Hi.
Yes, please.
I'm wondering the intuition why you divide the images as the scales, like the scales you designed.
I guess the intuition is that we know that generating a small image is easier than generating a large image. So splitting up the problem is kind of a natural way to decompose the problem into first generating a low resolution image and then upscaling it. It's kind of like splitting it up into low resolution generation and kind of super resolution, if you like.
Okay, thanks.
Earlier, you mentioned something about the likelihood not being impacted, but the sampling being better. Can you say a few more words on that?
Yeah. I don't really know what the intuition is there. I guess we know that if you kind of compare different model classes by likelihood, then it's kind of hard to say for sure what that means for sample quality. And I think this is probably just maybe an instance of that phenomenon. I don't know for sure, but that's my off-the-cuff guess.
Thank you.
Cool, thank you. Oh, one more? Do we have time?
Yeah.
Cool.
How much time is needed to generate one image in this model?
It's hard to give a meaningful answer to that question because we have kind of a sketchy research implementation, and if you wanted to actually tune these things to be fast, it could be, many multiples of a difference in speed. So it's hard to say.
Yeah. Thank you.
All right, let's thank the speaker again. Our next talk is dense bundle adjustment networks, and Chenju is the speaker.
Okay. Thank you for having me here. My name is Chenju Tang, currently a final year PhD student from Simon Fraser University with Dr. Ping Tan. Today, I will introduce our work, dense bundle adjustment networks. Different with the previous and next presentations that are about generating natural images, our work is about 3D reconstructions. It is an inverse problem that recovers the 3D models and camera poses from a given set of images. And bundle adjustment is the golden standard algorithm for 3D reconstruction. It usually starts by matching a set of feature points between images. And then solve for the 3D points and camera poses by minimizing the distance between actually matched feature points and the rays that originate from the corresponding 3D points. And the solution to this minimization problem will be the expected 3D points and camera poses. However, feature matching is difficult, especially in scene that containing repetitive patterns or lacking textures, which will introduce a large amount of outliers and make some minimization fail. So recently, some researchers proposed a photometric bound adjustment that receives a set of video frames, but skips the feature matching and directly minimizing the pixel intensity difference between the projected points. After the pixel intensity difference is minimized, then we can have semi-dense 3D maps and the camera poses. However, there is no free lunch. The pixel intensity difference is a highly non-convex object functions and makes the minimization more sensitive to initialization. In this work, we integrate bound adjustment in a convolutional network, a neural network as a layer. We want to maintain the multiple geometry through the bound adjustment optimizations. Meanwhile, we want to use the CNNs to address the problems that in the conventional algorithms. So it is necessary to make the bound adjustment differentiable for end-to-end training. With this bound adjustment layer, we can learn a feature pyramid to replace the pixel intensities in the photometric bound adjustment. And the feature pyramid will help to define a better object function that is easier to minimize. Besides the feature pyramid, we also use a standard encoder-decoder structure to learn a set of basis steps and represent the final depths as a linear combination of these spaces. This parameterization will reduce the number of unknowns to solve and will also regularize both the training and the inference. So let's go back to the bound adjustment layer to see how to achieve the differentiability and that enables the other part. In our method, the bound adjustment solve for the camera pose and 3D points by minimizing the feature difference between the projected points. We can rewrite these minimization procedures as a function. But unfortunately, this function is non-differentiable. The reason is that the bound adjustment is usually solved by the Levenberg-Marquardt algorithm iteratively, and at each iteration, an incremental update to the current solution is solved. The optimization is considered to be converged and terminates when the magnitude of the incremental update is smaller than a threshold. And this terminate strategy results in the first non-differentiability. In addition, the damping factor is also adaptively adjusted. If the objective value is increased, then the damping factor will also increase to have stronger regularization. Otherwise, it will decrease. This damping strategy leads to the second non-differentiability. To fix the first non-differentiabilities, we follow the paper generic optimization-based modeling by Justin Domk in 2012 to run the iteration for a fixed number. To fix the second non-differentiability, we propose to predict the damping factor lambda using an MLP from a set of features. To construct the features for the damping factor lambda prediction, we calculate the current objective value at each pixels on each channels. And then we use global average pooling to convert these multi-channel feature error maps to feature vectors and feed it forward to an MLP to predict the damping factor lambda. And the intuition is that the objective value will evaluate the quality of the current solution and decide how large the damping factor should be. Now we have the differentiable bound adjustment. Then we are able to learn a feature pyramid to define a better objective function to minimize. To give an intuition about how this learned feature pyramid helps the bound adjustment optimizations, we visualize the objective value on a single point that is defined over the raw RGB values or the pre-trained features on the ImageNet and the features that is trained specifically for bound adjustment. It is clearly to see that the objective function defined the raw RGB values is highly non-convex. This is why the photometric bound adjustment is sensitive to initialization as just introduced. And the objective function defined the pre-trained ImageNet features are flat, which may cause slow convergence, while our learned feature specifically for bound adjustment is closer to a convex shape. Using this feature pyramid, we can skip the feature matching as in photometric bound adjustments, but also we have a better objective function, and that is less sensitive to initialization than the photometric bound adjustment. Besides a better objective function, we also use the CNN to learn the parameterization of the depth maps. We represent the depth as a linear combination of a set of basis depth maps. And so for the linear combination coefficient in the bound adjustment, a similar idea was adopted by CodeSlam in the last year's CVPR, but our basis steps is learned from a standard decoder structure with a shared backbone network with the feature pyramids, and they are also learned jointly end-to-end. The basis steps guarantee that the final depth will especially smooth. It will not only handle the difficulties in the flatter region, such as walls and tables during inference, but also it helps to make sure that the projected point stays within the images and make sure that the loss can be back-propagated during the training. So the intuition behind this parameterization is that a scene is usually composed of standalone objects and the general layouts. We expect the network can make the basis to make some basis focus on the objects, while the other basis focus on the depth, the general layout. And it is interesting to see that the network can actually learn this concept implicitly. So in summary, our BANet contains three main components. First, a differentiable bound adjustment layer that enables end-to-end trainings. Second, a feature pyramid that helps to define an object function that is easier to optimize. And finally, basis depth maps that helps to reparameterize the solution and regularize the training and inference. Of course, our work is not the first that use CNNs for 3D reconstructions. However, some previous works, they completely ignore the multi-view geometry knowledge during inference. They only use the multi-view geometry constraint as a loss during training and expect the CNN can rediscover the multi-view geometry through training, but it is very hard to verify because CNN is black box. For examples, one work, DemoNet, from the CVPR 2017, predicts the depths and camera poses from two separate branches, while another work from the same year CVPR predicts the camera poses and 3D points from two separate networks. Instead, some other works maintain the multi-view geometries through optimizations. However, some of them are not end-to-end trainable, such as the CodeSlam, or can only handle two images, such as the AirSnet, or even only use multiple geometry partially, like the LKVO learners. And in addition, all these works use the photometric arrow as the object functions, which is sensitive to initialization as just introduced. Different from all these works, we are the first to achieve the end-to-end training and maintain the multi-view geometry at the same time. Since our work is more about the newly proposed model, so we use the following commonly used loss to train the network. First, rotation loss that is defined over the camera rotation cotannian vectors, a translation loss that is defined over translation vectors, and depth loss that is defined over Bahu whole depth law that define over depth values similar to the Liana for single view depth estimations. We first evaluate our method on the indoor scanner dataset. It's clear to see that our method outperforms the traditional algorithms as well as outperforms the DemoNet, which is another CNN-based method. We also evaluate our method on the outdoor Kitty dataset, which achieve better performance than the unsupervised camera motion and depth estimation method because we use the feature metric arrow, and also better than the molecular depth estimation method because we have multi-view here to have stronger information. And all the previous results are generated on 2 views, which is here we demonstrate our capability on multiple views. It's clear to see that when more views are included, the performance consistently getting better. So the conclusion is that in this paper, we propose a differentiable boundary adjustment layer that enable learn the feature pyramid as a better object functions and learn the basic depth maps to regularize the training and inference. We have achieved better performance than other CNN-based methods, but we still have some limitations, like we can't handle large camera motion. And at last, because our work is specifically for 3D reconstructions, we want to share some more general principles that may be helpful for people working on other topics first. Okay, thank you. See you at the poster. So.
We have a couple of minutes for questions. So I have a bunch of questions. One is, when you compare with this SFM learner in a test set, does the SFM learner is allowed to fine-tune on the test set, or you just use inductive setup where you train on trainings and then you just fire the network from Tinhuizu? And if you would allow to fine-tune, do you think it would get better?
So fine-tune the SFM learner? Right, because we actually trained on the same data set like the kitties, because the kitty result is trained specifically for kitty. So I think the training data is the same.
Right. So what you're saying is you don't allow to fine-tune. The other question is this large camera motion constraint.
Yes.
Is that because we don't handle visibility and occlusion somehow?
Yeah, yeah.
Right?
Oh, yeah, yes. Actually, in following up, I'm currently working on that. I found that actually its occlusion is handled implicitly by the features. So the features will just learn a metric that is robust to the occlusion.
Great. Also, the paper has a lot of ablations. The one ablation I didn't find is about the depth map representation versus just fine-tuning a full dense depth map network.
Okay, yeah. It's interesting because as one limitation is that because currently the depth basis is generated from the single image. So actually in the ablation study, we can see that the performance gain from the multi-view optimization is not that large. So this is also what I'm currently working on to improve that.
Okay, let's thank the speaker again. So the next talk is large-scale gun training for high-fidelity natural images. Andrew Brock is the presenter.
Timer out. All right, thank you very much. My name is Andy Brock. I'm with the Edinburgh Center for Robotics. This is joint work that I did with, pardon me, with Jeff and Kren during my internship at DeepMind. So I'm here today to talk to you about BigGAN, and we'll cut right to the chase. The end result is that we have really nice, high-quality samples These are conditional ImageNet samples generated at 256 pixel resolution. They achieve pretty high inception scores and pretty low FIDs, which are two metrics that we tend to use in the GAN community for evaluating the quality of our generated images. They're flawed, and we're working on better ones, but right now that's kind of the state of the art as far as figuring these things out. So I'll talk a little bit about why these images look the way they do, things they're good at, things they're bad at, and what we can learn from all this work. A common question that comes up when people see our good samples is, does it not just memorize the training data? And as far as we can tell, it does not. So we measure nearest neighbors in pixel space, in VGG space, in ResNet space, and we don't find any nearest neighbors that actually look like the exact images we generate. No one asks that questions when they see our bad samples, so that might also indicate a little bit. Another way I like to test the quality of generative models is generally with interpolations. Smooth, meaningful interpolations suggest to me that my model has actually learned the manifold of the natural images I'm trying to generate. So for example, we see dog to frog looks pretty good. Salt shaker to geyser passes through meerkat, just like in nature. And we have pretty good insect interpolations as well. So the bottom is a Z conditional interpolation that only interpolates the latent, but keeps the class conditioning constant. Or sorry, interpolates the class, but keeps the latent constant. Got that backwards. So what is the general motivation for why we are building these things? Why are we building bigger models? Why are we building big GANs? And my personal motivation is kind of an unsupervised learning idea that if a model understands the data, or if a model can draw the data or generate the data, it has to, on some level, understand it. And the level at which that understanding exists depends on the inductive biases of your model, depends on exactly how you have it generate the data, and it depends on the rest of your training setup. So when I say understand, I mean that in a very limited sense. So for example, a model that's trained on video will have different inductive biases, will understand things differently from a model trained entirely on still images. And we'll see a little bit of the cause and effect that comes into play as a result of that. So just the basics, if you're not familiar with GANs, we're going to formulate generative modeling as a two-player game where we have one network, the generator, that seeks to generate realistic image data or realistic data, and another model, the discriminator or the critic or the teacher, which attempts to distinguish between real data and sampled data. We have this nice objective function that we minimize via alternating gradient descent. And for this setup, we're going to be training on class conditional ImageNet, which is about 1,000 classes and around 1.2 million images. So the methods that we explore in this paper are going to build on a ton of previous GAN work that's kind of risen up over the last couple of years. We're going to explore fundamental design choices in the choice of the latent space in our priors and how we pass conditioning to the model. And we're going to scale upwards and upwards and upwards with TPU pods. We train on up to 512 TPU cores. So our model starts with a baseline self-attention GAN, which is just a residual network GAN that has a nice little self-attention layer in both the generator and the discriminator. That's from Zhang 2018. We're going to increase the batch size. So we're going to take this up from 64 to 2048. And we actually test even beyond this, but past that point, it doesn't make that big of a difference. And the reason this is important and why we think this helps is that when we're training on these large, diverse data sets like ImageNet, where we not only have 1,000 classes, but we have inter-class variation in all these different modes, if you only train with a batch size of 64, then you're sampling a very, very small number of these modes every time you do this wildly chaotic gradient descent procedure for your GAN. So we find that just kicking it up so that you at least get, on average, 2 examples per class per mini batch really, really helps to not only accelerate convergence, but just to improve coverage in general. We're going to make the models a lot bigger. So previous GANs that were used in this setting only had around maybe 43 million parameters. We're going to kick that up. And this is a pretty simple intuition, is that our models need to have a lot of capacity in order to capture all of the complex correlations and visual artifacts that occur in the data set. We're going to use parallelism to make it so that this is tractable. And we're going to use some scaling tricks. So the first and biggest one is that we use shared embeddings. So rather than having a single embedding layer for every single class at every single batch norm layer, as was previously done, we're just going to have a single learned 128-dimensional embedding that we then project to every conditioning layer. We're also going to use a hierarchical latent space with skip connections to all of the blocks in the generator. If you've seen some follow-up work like Style GAN, they use basically this exact same idea. So there's 3 papers at the same time. There's this Style GAN and one other paper that's here at ICLR as well, which I'm just blanking on the name of, I'm so sorry, that all kind of at the same time come up with the same idea. We're also going to make our models deeper, so we introduce a new architecture that's called Big GAN Deep that is 4 times as deep, but because of parametric and compute efficiency, actually has fewer parameters than its non-deep cousin. And this network just tends to work a little bit better as well. So the first thing we do is explore latent spaces. Pretty much every GAN has employed either a Gaussian or a uniform as the prior, as the distribution we sample the Z from. But we question whether or not this is optimal. And so we explore the orchard of latent spaces. We explore around 17, and we find some low-hanging fruit, some nice fruit there, pieces of fruit. And we find 2 that work pretty well. The first is just a Bernoulli, so just having a discrete latent. And then the sensor normal, or a ReLU normal, which is like a Gaussian. It's like a truncated Gaussian, but it has some sparsity to it as well, so you have a 50% chance to end up with a 0. We find that these both work very well, and we explore these in a little bit more depth in the paper. But we noticed while debugging that sampling from a truncated normal, where you resample any values that fall outside some truncation threshold, immediately improve the scores and the sample quality of a model trained with a standard normal. So this leads to the truncation trick. The idea that as you decrease the variance of the input to your generator, you're also going to decrease the variance of its outputs. And this allows us to have fine-grained control over the trade-off between sample variety and sample fidelity on an individual sample level. This visualization shows what happens as we truncate the input distribution. We start with a bunch of very diverse images, which maybe have some images on the tail that are lower quality. And as we truncate towards the mode, we end up with a single image because we have no variance. So we'll have the same sample every single time when we feed it all zeros. This can be thought of as literally the mode image of our generator. And one more set of examples for this. These are at 128 by 128 pixels as we go towards like the epitome of dog or the prime dog. So the truncation trick also introduces this nice property that our models now have this trade-off that's analogous to a precision recall trade-off that we're going to very, very messily measure with FID and inception score, where FID kind of indicates that you have more variety. If you have a lower FID, it just basically says you're better matching the variances in some feature space. And inception score kind of says you have higher fidelity. These are very, very loose. But you do see a curve that looks a lot like a precision recall curve, where as we increase truncation, we initially get a little bit of a boost in the FID because it does give you points for fidelity, but then as we lose all variety, that score basically goes down to 0, and we end up with a single image, which probably looks pretty good, gets a high inception score, but of course there's no actual variety to it. One other thing we find at scale is that we have instabilities that emerge for models which were previously stable. So settings which otherwise would have been stable out to 1 million iterations start to explode. So we investigate the top singular values in each layer. This is following on analysis from the spectral norm GAN paper here last year. And we just look at the top couple spectral norms, singular values. And the spectral norm actually is the first thing you want to look at that gives you a really obvious point where when the model collapses, the spectral norm of a couple layers explode in the generator and get a little hop, skip, and a jump in the discriminator. So we dug deep into why this was happening and tried to see if there's anything we could do to alleviate this. And we spent a bunch of time trying to regularize the generator without much success, but we found that if we regularize the discriminator, either with gradient penalties, some very carefully tuned dropout, or orthogonal regularization, we can prevent this training collapse. So we can make it so that our models kind of stay where they arrive at. They smoothly converge there. But this comes at a really sharp cost in performance, maybe like 40% reduction in inception score and FID, or increase in FID. So we have a pretty in-depth analysis in the paper as to why we think this might be that I don't really have a whole lot of time to get into. But the basic idea is that there's a lot of interactions that come through the adversarial game that make it so that preventing this collapse is sort of non-trivial if you want to do it without any cost to performance. Something else we observe is, of course, we can study these models post hoc and see what do they learn and what kind of things do we see in the samples. So my favorite failure mode that we find here is JPEGification. There's definitely some sort of JPEG vector somewhere in the model because, of course, not every image in ImageNet is high res. So if we upscale these low resolution images, or if we have an image which has a lot of JPEG artifacts because it truncates the DCT, then JPEG will actually show up as something the model learns to generate. Something else we see is that we interpolate between these two images on the bottom row here. We have one image of one rooster and one image of two roosters. You might think that a model which perhaps was trained on video or had some sort of causal understanding would introduce another rooster that walks into the image. But of course, this model was only trained on still images and doesn't have any of that kind of understanding, so instead it does what actually happens in nature and performs mitosis, splitting the two roosters out of the original initial rooster. Another failure mode we observe, which is pretty novel as far as I can tell, is what we call class leakage, where these models, which essentially are statistical models of visual co-occurrence, learn things like dogs are fuzzy and tennis balls are fuzzy, and therefore tennis balls are dogs. This leads to dog ball, you get cat flowers, you get all sorts of interesting things early on in training. Later in training, these tend to go away. We don't see too many of these in the finished product. But it's interesting to see these overlaps in things where you end up getting a lot of different faces of dogs stuck onto things which normally don't have faces of dogs because they're inanimate objects. We also see early on when the model is initially learning global structure, you get lots of nice double pugs that are kind of stitched together. So what's next? I think in general, where we need to go with this kind of work is to improve efficiency. So Moore's law is kind of irrevocably broken, and if we want to scale upwards, we can't really rely on having faster and faster processors every single year. We want better priors, so we explored this in an appendix, basically, and we explored the truncation trick. But I think generally the way we construct our latent spaces could be dramatically improved. We definitely need better metrics. There's a ton of people working on this. I really like a bunch of work on precision recall for generative models that's been out lately. And more dog ball, of course. I actually have dog ball stickers. If you come up and you want those, just come find me. I'm the guy in the whale shirt. And if you'd like more info, our paper's online. We actually have pre-trained models in Colab notebooks to let you run these. We just now have PyTorch 4 to 8 GPU training code that spoofs big batches with gradient accumulation. And our poster will be at Great Hall, BC, number 36. Thank you very much. Any questions? Yes.
Hi. What's the intuition after behind the different priors that you're trying? Were you just trying different ones just to see, or do you have some intuition?
No, it's a great question. So all of the priors that we tried do come from a particular design intuition. So in the case of the Bernoulli prior, these I actually think of them as priors, which we don't really talk about all that often. The Bernoulli prior reflects my belief that visual elements in our world are not simply all smooth things that vary between -1 and 1. There are discrete visual elements in the latent space, right? There are things like this is present or this feature is not present. The ReLU normal is also that. Features can be present or not present, but when they are present, they might have a variance in intensity. So we try a bunch of different ones that basically reflect this, like, okay, what do I think is the true prior that statistically describes the latent space? So yes, there is intuition behind all of those. Thanks. Yes.
Hi, thanks for your great talk. And probably my question would be very specific to your architecture design. And in your model, I saw that you applied spectral normalization to generator and discriminator at the same time. Mm-hmm. I think the spectral normalization trick really fits well in the discriminator side, but I cannot find any intuition about applying it to the generator. So I think regularizing the eigenvalues to discriminator makes sense, but I don't know what's the main intuition about applying that techniques in generator side.
Sure, so that's actually not something that we introduced. So there's a bunch of work out of Goodfellow's group at Brain that leads up to that, where there's first a paper that shows, by Augusto Sodena, where he shows that basically if you look at the Jacobian of the generator, right. They find that generator conditioning is causally correlated with GAN performance. There's a lot of other intuition I can get into about basically what you want is you want a well-conditioned generator that fills out the latent space so that every point in the latent space maps smoothly to a point in the output space. And that's basically the idea that comes into play with spectral norm, is that we don't want a generator where certain directions collapse, right? We don't want to have 18 different Z points that all map to a single output point. And spectral norm is a loose way of encouraging that.
Did you apply such kind of techniques that you just introduced to this model, and you could see the improvements after publish your paper?
So we do. So there are some papers here that do more in-depth spectral decomp, but we haven't had time yet. I've been back doing my thesis, so I haven't had time yet to test those in detail.
I see.
Thank you.
Thank you.
I think we have one over here.
Yeah. Can you give us an idea of the electricity bill to train such a network and how we could cut energy costs?
Sure, so this is something I think everybody should be aware of, right? Like you have to be aware of the environmental cost. There was some criticism early on. I would say that like in our case, our energy usage has been blown wildly out of proportion. And we are actually in general carbon neutral, like Google pays to offset all of these things. In my case, when I train this at home I train this just on my own back on a re-implementation on 8 GPUs that takes about 2 weeks to converge for 128 by 128 models. So however, if you spend that much time mining Bitcoin, probably about the same amount. I don't actually know the numbers on that, sorry. Thank you.
Thanks.
Do we have time for one more? Okay, one more.
All right, so very nice work. You did a lot of experiments, and most of them kind of worked out. Can you talk a little bit about the experiments that did not work out? What was a good idea that completely failed?
Yeah, absolutely. So we have a whole section on this in the appendix. We have a negative results section where we talk about the things where things didn't work out, and we're reasonably confident that we didn't like just totally screw up the implementation. It's also just a note that it's always dangerous to report negative results because you might like say, oh, this technique doesn't work, but in fact you just did it wrong. So it's something you have to be careful about with this. I spent a lot of time just trying to get like dilation factors in there. That was one. I spent a lot of time with different architectural choices that didn't work out. I'm just trying to think of what would be like the most interesting thing we tried that didn't work. We spent a lot of time trying to replace the early layers because when you look at the collapse in the spectrum, that happens basically entirely in the first linear layer in G, which is a wildly over-parameterized layer. It's a mapping from like 128 dimensions to 25,000 dimensions, so it's definitely over-complete. And we thought, well, clearly that's where the spectral norm explodes. That's got to be the problem. So we spent a bunch of time replacing that with small MLPs or with an MLP in a smaller convnet and basically saying like, here's the problem zone, can we spot treat this? And it turned out that nothing we did fixed that because that wasn't actually the cause of the problem. As far as we could tell, that was just the place where the cracks first showed in the facade. I honestly don't off the top of my head remember too many of the negative results, so that's maybe a good sign that we've moved past that, not really sure. But thank you.
Thank you.
Great, that concludes the session. Let's thank all the presenters.
Thank you.